redo all of that, but I'm not going to. What I'm going to do is I'm going to pause for 10 seconds. So if you're just joining us from home, this pause was brought to you by the good makers of coffee. All right, so anybody who's watching at home, way to actually answer the question. If we look here in this diagram, point P lies on the surface. It's where the ball was when it was struck. So we're looking a few instants after it's been struck, because clearly it's moved away from point P, and at this moment it has acquired some angular velocity, and we know that its linear velocity has been reduced by a small amount. But if I just look at this picture, the only force that can cause the only forces that are acting that could possibly be causing a torque on the system is friction. But friction acts in such a way that it can't cause a torque. Because although there's a torque arm clearly from here to here, that would be the torque arm R, and the force is being acted on at the end of that torque arm, that frictional force is acting at an angle of 0 degrees. So as a torque goes, it can't actually cause a change in the angular momentum. Moreover, the normal force and the weight cancel out. So they too can't cause a torque about point P. But just saying that the net torque is 0 isn't enough. They only give 1 point for saying that the net torque is 0. If we look at the answers, I should have been recording this. I didn't record any of the first part. That brings me great sadness. I would say I'd go back and degrade their FRQ. They now have at least access to that. Not that they couldn't have looked it up on the internet like you always do. Anyways, so here we go. I would point out that the next part, since you wanted to find the angular velocity, you're probably focused on net torque. So it should have seemed reasonable that you would have had something about the net torque acting in the system, and that should be equal to I alpha. There's only one torque, and that torque comes from friction, and this torque is positive because it is causing the object's velocity to increase. So that suggests that I would have R times the frictional force times the sine of 90 degrees, and that's going to be equal to 2/5 mr squared alpha. So plugging in for what I know friction is, I'm going to get R mu mg equals 2/5 mr squared alpha. I can cancel one of the r's, and I can cancel one of the m's, and solve this for alpha. This isn't the answer, but again, this proves something that I think we're going to need. We're going to get 5 mu g over 2r is the expression for alpha, which again is a constant, which means that our acceleration is a constant. I don't have to worry too much, if I don't want to, about converting this into a differential equation. I could use omega equals alpha t plus omega naught. Doing my substitution, I'm going to get omega equals 5 mu g over 2r t, and omega naught is 0. So it was asked, what if I didn't put 0 in for my relationship? Would I get a point taken off? In third period, I was feeling more generous because I was in a terrible mood. But, I don't know if they give you the point or not. They do expressly indicate here that mu naught is 0, as it's indicated in the problem. So, I kind of want to say that you have to have the 0 here, but I allowed the point in third period, so I'd have to allow it here. But there's 4 points, one for any use of the motion equation, one for use of Newton's second law according to torque, one for properly calculating the torque, and then one for bringing it all together. All right? Questions to this point? 8 points. So for you guys keeping track at home, 8 points means that you've passed the exam. That's right. Now, if you don't have 8 points right now, and I'm looking across the room, it looks like there might be 1 or 2 of you who don't have 8 points right now. I am crying for you a little bit on the inside, but on the outside, I'm just laughing at you like normal. Like normal. Ha ha ha, hee hee hee, ho ho ho. All right, so let's move right along. We're going to do part C, where it asks for us to determine at which time the ball begins rolling without slipping. And this is that one of those times where, I think it a prudent that we remember the conditions for rolling. And the conditions for rolling is when our linear velocity and our angular velocity are synchronized. Now, it's funny because they give a point, and somebody brought this up, where they say specifically the slipping stops when the tangential velocity is equal to the velocity of the center of mass. I don't think you need a separate point for that as long as you are using V equals omega r. I never talked a lot about, having to compare the center of mass velocity with the tangential velocity. We talked about it, but mostly in passing. This isn't the answer, though. This is where you start. You have an expression for both V and omega. And so we know that omega is increasing. It's increasing by 5 mu g over 2r times t. It's increasing, while at the same time, the linear velocity is decreasing. So we are looking for the time at which these are equal. So if I set these things equal to each other and solve for t, that should give me how long it takes until the system is rolling. The other problem we did a couple months ago, they want how far it went. We had to solve the time and then use that to figure out how far. But in this one, they just wanted to know when it started rolling. So we're going to solve this for t. You just got to do a little algebra here. You can cancel the r's over there. When you do the algebra, you're going to get that the period at which it begins to roll is v naught over mu g. That's just doing the the algebra. It's also written right there. 4 points for that. They give 1 point for the answer, of course, but there's a point for recognizing that the edge of the disc has to be going the same speed of the ball. I think if you use that, you're going to get that point too. And then by making your substitutions to show that they're equal and solving for t. That gets us to 12 points. That's the threshold of a 5. We are fully deep into 4 territory. If you're above a 10 right now, you're just rocking this one all the way. But what's funny is having given this as a quiz, performance has been usually lackluster on this one as a quiz. So I don't know what your performance looks like. I'm going to know probably today by 1:30 or so, but for right now, I'm hoping that's not so bad. Question D, though, I think strikes an interesting question, and they give 3 points for this explanation. It says, when the ball is struck, it acquires an angular momentum about the fixed point P on the surface of the table. During the subsequent motion, the angular momentum about point P remains constant despite the frictional force. Explain why this is so. And I really love this question because we could prove that it's constant. We have everything we need to prove it's constant. Now, third period was not interested in this even a little bit. And judging by the 4 people who are looking at me, I'm not sure how interested you guys are either. But there is a fairly straightforward. They give 0.1 for saying that the net torque about point P is 0. That's worth 1 point. Then saying that because the net torque is 0, the angular acceleration is 0 is another point. And then saying that because the angular acceleration is 0, the angular momentum has to be constant. That's the third point. They required a full connection, meaning you had to connect the dots. You can't just say net torque is 0, therefore. They want you to be able to say that if the net torque is 0, the acceleration is 0, and if the acceleration is 0, the momentum is constant. It's a lot more they're asking of you. So, this kind of, even though this test was 1980, it's clear that even back in 1980, they wanted to make sure that you understood that just saying something is true isn't enough to be able to garner the points. They want you to explain it. Explain it means connecting all the way until you say the theoretical thing they're asking for, which is the momentum is constant. So if you don't state that the angular momentum is constant due to no angular acceleration, you're probably not able to get all 3 points. Now, in the participant window, did anybody prove that it's constant? Let me ask it this way. So before you answer in the participant window, just so you guys who are actually paying attention, because I can see your little eyeballs, this is where we stop the whole thing to see if anybody out there is actually listening. So that's what we're doing right here, because you guys could just shake your head, and I would know. But the other 20-something people, not so much. So for all of you viewers listening at home, Do you understand what I am asking when I'm asking if you proved it? Yes or no? Apparently only Ella's listening. Oh, now a few more people are listening. Wow, 21. 22. All right. Yeah, I don't have to hear from people that I can see, because I can always see the confusion on some people's face. Right, Sarah? Sophie? Karen? BK? All right, well, let me show you. This is what I mean when I say we can prove it. And I'm not going to go through the whole thing because of two reasons. One, I want to get to today's lesson. And while I'm getting this set up, I'm going to draw a few things. What I would like you to do is make sure you've added your total out of 15. And before 1:30 today, please submit it over Edsby. I want to take a look at your scores. So if you already submitted it like I had asked, great. I'm looking at it now with all the red on it. So you don't have to do it this minute, but please make sure that sometime before the end of the day today, I get a chance to see it. Okay, so now that I have you all back, you could prove that it has a constant angular momentum. Now, I have not yet gone about the task of proving it, but I want you to think about what it would take to prove it. First, consider that when it was initially struck, when the ball was still right here at point P, the instant that it was struck, the ball had a velocity v naught. It had no angular speed, so currently omega naught is 0, and it was on point P. So if this is my initial condition, at this instant, the angular momentum of the ball would have to be r cross P. That is the definition of angular momentum. And I'm using P as my point of reference, which would mean that at this instant, the angular momentum of the system is r m v naught. Now, our supposition that we state by not a proof, but by an explanation, is that this remains constant because there's no unbalanced torque acting in the system. On the other hand, after some point in the future, the object is actually located a distance r away. And it currently has an angular velocity, omega, and it currently has a linear velocity, v sub t, which suggests that currently its angular momentum is going to be the combination of its point mass angular momentum about point P plus its angular momentum about its own center of mass. Right? Well, this has got to be r times m v sub t, or v as a function of t, times sine of phi. All of that has to be this, plus I omega as a function of t. That has to be its angular momentum now. Well, we could plug everything in and see if it equals this. I bet it does. Now, I'm not going to do this. It's an interesting exercise, maybe not a great exercise. And if there's a super smart person in the room, and I know there's some smart people in this room, they're all a lot smarter than I am. I know. Senior test scores. There might be something you have to do here to actually make a correction for point P. This one's okay. And if you're sharp, you realize you're not going to actually use R. You're probably going to use this distance, x, of which there might be a motion equation that we could use to describe how fast it's traveling and where it is over time. And you're probably going to use R and not use this. And you're probably also going to use something like that for sine. If you see where I'm going, you might see that you could rewrite part of this. And we've talked about this, meaning you could write this as R m v as a function of t times r over r. You see where I'm going, right? A little of it. The other thing, though, is what would you use for I here? That might be a little bit more difficult because we're doing I relative to point P. You see why that might be trouble, right? Like not I about center of mass, but I about point P. That might be a little bit more challenging. But it's something to think about. I'm going to leave it there because I need to answer something from yesterday. And I also need to tell you guys something about rotational mechanics and angular momentum. Because you kind of have to over here. So I recommended that you do it over here. In fact, I think I even set you up with some of that by saying, consider that the dart, with its velocity and its mass, and knowing that it's going to strike at a distance L away from the pivot point, would have an angular momentum of mvl. That would have to be its angular momentum relative to the pivot point. And that when it strikes the mass, the angular momentum of that system could be expressed as 3m L squared omega. All of this being I times omega. I would have to use the I for a point mass, and the mass is now 3m because the box was 2m on its own, and now the dart being embedded in it makes it 3m. Suggesting that these would have to be equal, and this could give you an expression for the angular speed. Now, that could lead you to get an expression for the angular kinetic energy. So you could easily take this and have the rotational kinetic energy from that. Now our problem is still dealing with potential energy. Our potential energy is still going to be based on the height that this system attains relative to the ground. We can't really talk about torque or anything like that here because the torque is acting at a different angle all the time, and that would be tough. On the other hand, the original example where you had to deal with angular momentum, this one, you should be aware that the center of mass is being lifted when you calculate its change in potential energy. And since we're about to get yeeted, you guys have a wonderful day today, and perhaps come up with an expression for 1 minus cosine theta for this, and be prepared to show me tomorrow, okay? In class, sometime around, noonish. Well, it's been wonderful seeing you. I hope you all have a wonderful day, and I look forward to seeing you all tomorrow. So go out there outside. It's really nasty and hot and yucky out there, so have a great day. Love you all. Bye-bye.